In this chapter, we're going to go over the law of large numbers and the expected value. The law of large numbers is basically the idea where if the process is repeated through many trials, the proportion or the percentage of the trials in which event A occurs will be close to the actual theoretical probability. So, in other words, we're basically saying that the relative frequency method for probabilities should, given enough observations, should get closer and closer to the theoretical approach for probabilities. So, a couple lectures ago, I had mentioned that if we were to flip the coin about 5 times, and I basically just gave an example where 4 of the 5 times ended up being heads, so the probability of getting heads was about 80%. However, what if we were to flip the coin 500 times or 1,000 times or even more? In 500 coin flips, you might not get exactly 250 heads and 250 tails, but we would expect that the probability of getting heads out of those 500 coin flips should be fairly close to 250 times, or the percentage should be close to 50%. And the idea is that the more coin flips we actually do, the closer and closer it will get to the theoretical probability, which is 50%. So I mentioned something about expecting to get about 250 heads, right? So we have what's called an expected value. So let's suppose that you have two more events and that each event has its own value and probability. So in other words, it could be the same, like heads and tails have 50-50. You could have something where you have 25% chance of winning and then 75% chance of losing, and so on. So to figure out the expected value, we end up using this formula where we basically sum all of the probabilities times their own values. Suppose you are playing my dice rolling game, and you lose when you roll a 1, 2, 3, or 4, and you pay $3. However, you win $5 from me if you roll a 5 or a 6. What is the expected value of playing this game once? Now, of course, assuming that everything's fair and that there's no cheating, we need to look at the two different values and their probabilities. So if you pay $3, that would be a negative dollar amount for you. And what's the probability of paying me $3? Well, that would be if you had rolled a 1, 2, 3, or a 4. So the probability of losing, so the probability of losing in that case would end up being 4 out of the 6. Now, you would win $5 if you actually win, right? So it's $5 times the probability of winning. So the probability of winning is getting a 5 or a 6. So the actual probability is 2/6. Calculating this, and we end up getting negative $0.33. So another way of thinking of the expected value is you can kind of think of this as the mean. So this is the average amount that you would expect to win or lose for every game. What does this really tell us? Does this seem like it's a game worth playing here? Well, if on average you would expect to lose 33 cents, that doesn't really seem like it's a very fair game, or at least not a good game for you to play. Now, if you were to play this game 100 times, how much money would you expect to win or lose? Well, if the average amount is 33 cents per game, and we have 100 games, then we would just take 33 cents times the 100 games, and that'd have a total of $33. Now, keep in mind that these are negative values, so you'd expect to lose about $33. Is this exactly how much you're going to lose in 100 games? Possibly not, right? And especially in one game, you will either win $5 or lose $3. You cannot lose 33 cents in just one game. Again, this is an average amount. So it could be that you end up having a nice winning streak and maybe you end up making more money than negative $33, or perhaps you are unlucky and end up losing more than $33. Now, if you were to extend this and play thousands and thousands of times, we would expect that the amount would kind of follow that law of large numbers. So you get closer to however many games you play times the negative 33 cents. So now let's talk about the money making game. So in The Legend of Zelda, there is a mini game called the money making game where you must select one of 3 rupees. Every time you play the game, the rupees are assigned either -10, -40, +20, or +50. Now, 1 rupee is always -10, 1 rupee is either -10 or -40, and the third will give you either 20 or 50 rupees in return. So basically, one of the 3 rupees will give you a winning amount. That winning amount happens to change from time to time. And the losing amounts will also change, where one of them is guaranteed to be -10, but the other one could be -10 or -40. And after doing some math, I found that these were the probabilities for each of these amounts. So we want to find the expected value for each of these. Well, I would simply just multiply all of these together, and then I would add up those together. So rounding each of these to 2 decimal places, I can go ahead and add all of these together. And after subtracting these, I end up with an answer of roughly -1.7. Now, there's a little bit of rounding error on this. I believe the actual answer ends up being -1.66 repeating. But this tells us on average, we would be losing about 1.7 rupees per game that we play in this money-making game. So is the money-making game worth playing? I would say no, it is not worth playing. There are other better ways of getting a hold of rupees, and you can actually get them for free. But also, because on average you would expect to lose about 1.7 rupees per game, that can add up over hundreds of games. So now for a more realistic example of where you'd actually use the expected value. So one case is trying to figure out how much you'd expect to win or lose in the local lottery or nationwide lottery or something of that nature. So suppose that $1 lottery tickets have the following probabilities and values given in the table below. And you're trying to calculate the expected value of a lottery ticket. Now, what's tricky about this that's different from the other examples is regardless of if you win or lose, you have to pay this $1. So that means that if you win $1,000,000, you still paid $1 to get that $1,000,000. So you actually had a net gain of $999,999. So keep that in mind that you do have to include purchasing the ticket. So that's what makes this different from some of the other examples we've looked at. So that's what makes this different from some of the other examples we've looked at. So now I'm going to go ahead and just multiply all of these together. And in this case, we end up getting an expected value of -64 cents. There is a term called gambler's fallacy. And this basically is the mistaken belief that a streak of bad luck makes a person due for a streak of good luck. Now, the reason why this is a fallacy is because of independent events. In the last section, we talked about independent events as being 2 events that, if one event occurs, that does not affect the probability of the other event to occur. And this is basically what's happening with the gambler's fallacy. Even though if they've previously lost the last 100 games of, say, the Powerball, for example, that does not mean that their next time that they buy a ticket will improve their chances. Now, of course, this is assuming that they wait until the drawing and then they buy a ticket, and then wait for the next drawing and then buy a ticket. Of course, with the Powerball, you could actually buy several tickets and improve your odds because you have more numbers to work with. So even though this is a quiz problem, I think this is worth going through to make sure that we all understand how to find the expected value. We want to find the expected value for the company per policy sold. So this insurance policy sells for $1,000, and we have all of these different odds for how the company will lose money. Making a small table here, I'm going to write the dollar amounts that the company makes or loses, and then I'm going to write the probabilities of those dollar amounts. So the company makes $1,000, and that ends up being 100%, or 1. Now, of course, if we have 1 in 50 that file a $10,000 claim, or in other words, that is 2%, or 0.02, then the company will lose 25,000. And 1 in 250 chance, the company will end up paying $60,000. So 1 out of 250 is 0.004. So multiplying those together, and we end up with the following. So after taking 1,000 minus 500 minus 240, and we find out that the company is making $260 per customer. So this is the expected value. So if they were to take that times 10,000, how much would they end up profiting in that case? So if they had 10,000 customers, that means that they actually make 2.6 million. Now, of course, these probabilities are probably not very definitive. In fact, they could very much change depending on the type of insurance and what happens around the world. So let's say that this is for house insurance. Could be that there ends up being a tornado that destroys tons of houses, in which case uh, it's most likely that the insurance company loses quite a bit of money from that. Another example where you can use the expected value is looking at credit card companies. You'll oftentimes see uh, rewards that credit card companies are willing to give their clients or card holders, and that's mainly due to wanting to encourage people to own their credit card. And so, if you make enough rewards, you get some money back in the form of either gift cards or points or money added back to your balance, et cetera, et cetera. And the way they still make sure that they maintain money is by, again, calculating their expected value. Well, this is all I have for this slide, so thank you for watching.